Ever wondered about the tiny particles that make up the universe and their bizarre behavior? Well, welcome to the quantum world, a realm where the rules of classical physics cease to apply and the strange and the inexplicable become the norm. In the first lesson of Carlo Rovelli's 7 Brief Lessons on Physics, we encounter the concept of quantum superposition. This is a principle that allows particles to exist in multiple states simultaneously. Quite like Schrödinger's infamous cat, which is both alive and dead until observed. The same applies to particles in the quantum world. They can be in 2 places at once, spinning in 2 directions, or in any number of states until we observe them. Now, you might ask, how can something be in 2 places at once? It's mind-boggling, isn't it? But that's the beauty and mystery of quantum mechanics. It defies our everyday logic and understanding of the world. This peculiar behavior of particles is described by something called the wave function. Imagine a wave on the sea. It's not located at a single point, but spread over an area. Similarly, the wave function describes the probability of finding a particle in different states. It's like a cloud of possibilities spreading out and encompassing all the potential positions and states a particle could be in. But here's the catch. The moment we observe a particle, the wave function collapses. This means that the particle is no longer in a superposition of states. It chooses one state, one position. The act of observation brings the particle from a realm of possibilities into a definite reality. This strange dance between observation and reality is what makes quantum physics so fascinating and mind-bending. It's a world where nothing is certain until observed, where particles spring in and out of existence, and where the impossible becomes possible. So, the quantum world is a realm of possibilities, and observation is what brings reality into focus. It's a world that's as mysterious as it is beautiful, a world that continues to baffle and amaze us. Such is the magic and mystery of quantum physics. Have you ever thought about the fabric of the universe itself? Quite a provocative question, isn't it? Well, that's exactly what we're going to explore in this second brief lesson on general relativity. You see, general relativity is one of the pillars of modern physics, and it presents a radical new understanding of the very canvas of the universe. It tells us that space and time, 2 seemingly distinct entities, are in fact interwoven into a single entity known as space-time. Consider this. You're sitting in a room right now. You can move left or right, forward or backward, up or down. Those are your 3 dimensions of space. But there's also another dimension you're moving in, time. You're constantly moving forward in time. This is our 4-dimensional space-time. But here's where it gets really interesting. According to general relativity, this space-time isn't flat, it's curved. And what causes this curvature? That's right, it's mass and energy. Imagine a trampoline. If you place a heavy ball in the middle, the trampoline bends around it. This is similar to how mass and energy bend space-time. The more mass or energy, the more space-time curves, and the stronger the gravity. That's why Earth, being quite massive, curves space-time around it, and we experience this as gravity pulling us down. But there's more. This curvature of space-time also influences the paths of objects moving through it. An object moving through curved space-time will follow a curved path. This is why planets orbit stars and why light from distant stars bends as it passes near the sun. These are all effects of the curvature of space-time. So when you drop an apple and it falls to the ground, it's not because there's a mysterious force pulling it down. It's because the Earth has curved the space-time around it, and the apple is simply following the natural curvature of space-time. In essence, gravity is not a force acting across space, but a shaping of space and time around matter. Ever contemplated the vastness of the cosmos and our place in it? This third lesson takes us on a journey through the grand architecture of the cosmos. Let's start with the Big Bang Theory, which posits that our universe began as an infinitesimally small, hot and dense point around 13.8 billion years ago. From this fiery origin, the universe has been expanding ever since, like a balloon being blown up. This expansion isn't just a theory, it's supported by a phenomenon known as cosmic background radiation. Imagine this as the afterglow of creation, the remnants of the heat from the Big Bang still detectable today. It's a kind of cosmic hum, a whisper from the universe's fiery past that fills all of space. That's right, we're not just in the universe, but of the universe, made from the very stuff that was there at the beginning. So we are part of a cosmic story, with the universe still unfolding its chapters. Ever wondered what everything around you is made of? Well, deep within the heart of matter lie minuscule building blocks known as elementary particles. These are the fundamental constituents of the universe. There are two types of elementary particles, quarks and leptons. Quarks bond together to form protons and neutrons, which make up the nucleus of an atom. Leptons, on the other hand, include electrons that orbit the nucleus and neutrinos, ghostly particles that rarely interact with matter. Then there are the force-carrying particles, the ones responsible for the four fundamental forces of nature: gravity, electromagnetism, and the strong and weak nuclear forces. These particles mediate interactions between quarks and leptons, holding atoms together and governing the behavior of matter on both the smallest and largest scales. The interplay of these particles and forces weaves the very fabric of the universe. From the tiniest speck of dust to the grandeur of galaxies, everything is a result of these intricate interactions. In essence, the universe at its most fundamental level is a symphony of particles and forces. What happens when quantum mechanics meets gravity? This question leads us down the rabbit hole of the enigma that is quantum gravity. It's the theoretical attempt to reconcile the peculiarities of quantum mechanics with its particles popping in and out of existence and the expansive scale of general relativity, which governs the planets, stars, and galaxies. Quantum gravity is like the missing piece of a jigsaw puzzle, a piece that could explain the fabric of our universe. But finding that piece is no easy task. There are still many problems to be solved, many questions unanswered. We're wrestling with the fundamental nature of reality itself, trying to decipher the cosmic code. The significance of this quest can't be overstated. Imagine understanding the universe at its most fundamental level, unlocking the secrets of black holes, the Big Bang, and even the nature of space and time. That's the promise of quantum gravity. So quantum gravity remains one of the greatest unsolved mysteries in physics. What's the connection between time and heat? This question takes us on a journey into the sixth lesson on the fascinating world of thermodynamics and the arrow of time. The arrow of time, as it's known, isn't an actual arrow you'd see on a clock, but rather a concept that represents the one-way direction of time. Now, let's add heat to the mix. Thermodynamics, in simple terms, is the study of energy, heat, and work and their interrelation. It introduces us to a concept known as entropy, which is essentially a measure of disorder or randomness in a system. So how do time and heat come together? Let's picture a cup of hot coffee sitting in a cooler room. Over time, the heat from the coffee disperses, warming up the room slightly while the coffee itself cools down. This is an example of an increase in entropy, the heat energy spreading out, creating a more disorderly, more random state. And here's the crux of it all. This process is irreversible. You won't see the room's heat spontaneously gathering back into the coffee, returning it to its original hot state. This irreversibility is the arrow of time in action. Time moves forward as entropy increases. In essence, the flow of time is the story of the universe's journey from order to disorder. How has our understanding of physics shaped us? This question brings us to our seventh lesson, exploring the profound impact of physics on humanity's worldview. Physics, in essence, is a quest for understanding, a pursuit of knowledge about the fundamental nature of reality. It's an endeavor that has taken us from the atomic to the cosmic, from the intricacies of quantum mechanics to the vastness of galaxies. This journey has profoundly altered our perception of reality and our place within it. Before physics, our ancestors looked at the stars and saw only distant, unattainable lights. Now, we understand those stars are suns, many like our own, each potentially hosting a myriad of planets. We've come to realize that we are not the center of the universe, but a small part of an inconceivably vast cosmos. Physics has also changed the way we perceive time. No longer a constant, unchanging entity, time is now understood to be flexible, intertwined with space itself. This concept, initially mind-boggling, has become a cornerstone of our understanding of the universe. On a more immediate level, the discoveries of physics have driven technological advancements that have transformed our daily lives. From the electricity that powers our homes to the computers and smartphones we can't imagine living without, all are products of our understanding of physics. So, as we unravel the secrets of the universe, we are also unraveling the secrets of our own existence.